So today it's my pleasure to invite Professor Qing Qu to give a talk, more a seminar talk on the, I think it's kind of very timely talk on the diffusion model, but shed more lights on the, some better understanding on the generalizability and some, semantic low dimension subspace or low rank property of diffusion model. So on MERL, we have a lot of interesting diffusion model from different perspective, speech, sensing, even I know like control, and definitely computer vision. So I hope this is very an interesting talk from to all the different teams. So very short bio. So Professor Qing Qu is an assistant professor at the University of Michigan. So he was a Morse known data science fellow at New York University from 2018 to 2020. So he got the PhD from Columbia University under John Wright back to 2018. With a lot of like awards, I think probably I want to mention this NS Career Awards in 2022, Amazon Research Award in 2023. His current research interest focus on deep representation learning and diffusion model. So with that, the floor is yours.
Thanks so much, Perry, for the great introduction and invitation. So today I want to talk about something on the generalization of this kind of generative model, diffusion models. I think there's a lot of work, recent theoretical work focused on sampling, but I think here I want to provide a different perspective to understand how diffusion model, when they train on finite number of samples, then they can generate creative or novel content different from the training data set and what enables this. And based on understanding, we can actually manipulate the generation of diffusion models, and then we can do many tasks like to better guide the generation of diffusion models. So first of all, I want to give you an overview of generative models. So I think in the past 5 years, right, so we see a tremendous growth of generative models, especially start from stable diffusion and the ChatGPT moment, right? But the generative models can be traced back to 2012 from this variational autoencoder. In other words, right, in vision, we saw GAN models, CLIP models, and stable diffusion really kick off the diffusion model business. And more recently, there's a lot of video diffusion, like the Sora model from OpenAI, and the DALI, this kind of text-to-image diffusion models. And in language, we have from this transformer to BERT and to ChatGPT, and more recently DeepSeek, right? There's all kinds of generative models in language and vision. But in this talk, I will more focus on the image and video generation, this diffusion models. So what is generative model, right? So the basic idea of generative model is like the following, right? So you want to learn a machine learning model that is from different modalities, like for example, image, audio, text, etc., right? But here you don't have any labels. You want to learn the distribution of the data. And once you learn a model, you're going to give a noise input, usually a Gaussian noise, for example, input the noise into the model. And then through the model, you will generate something. And our hope is that we can generate something kind of different from the training data, right? We can manipulate the generation. We can create something like different from the training data set. And toward this goal, I think the first idea is it's using this variational autoencoder. So the autoencoder, can be traced back to the early 90s. But originally, the autoencoder is that we are using a reconstruction loss, like we have an X input and then the output X hat. We want to reconstruct the original X. But the goal here for autoencoder is that we want to do data compression and representation learning. We want to compress data into a low-dimensional space, and we want to learn representations. But later on, people find that not only the encoder is very useful, but actually the decoder is also very useful. Encoder is for representation, and decoder is for generation. If you input a noise, actually the decoder can generate something quite meaningful. But unfortunately, for rational encoder, right, you are doing this representation and the generative model at the same time. You're not doing neither of them well, right? So, and the performance of rational encoder actually is not so good. And later on, people introduce this idea of generative adversarial networks. So the basic idea of generative adversarial networks is that you are going to generate using a generator, where you give a random seed and the generator will generate a fake image. And then you have a discriminator trying to distinguish between the real and the fake. And then you're going to play a like two-player game and then solving a minimax optimization problem. And so the GAN actually have much better performance than we, but the issue with GAN is that it's not very stable because you are solving a minimax problem. So minimax problem actually is very hard to find a settle point. And you will, like, people find that actually there's this kind of model collapse issue, right? So if you train the model on a very large data set, it's very hard to scale the model stable. Right? It's very unstable to train GAN. So that's why I think recently people are more interested in these diffusion models. So diffusion model is different from Wei and GAN is that diffusion model is not doing this one-step generation. So Wei and GAN, right? So basically you input noise and you pass through the neural network, and in one step you will generate the content. But diffusion model is different. So you will gradually remove the noise. Like starting from pure noise, right? You're gradually removing the noise until you generate something novel, something new. And later on, we'll see that actually the training loss of the diffusion model is much easier. Like it's just a least squares problem, right? It's much easier to minimize, to optimize, and that's why actually training the diffusion model is more stable, and you can scale it to large data set. And moreover, the diffusion model is also there are many ways to control the generation of diffusion model, right? So, for example, this kind of like stable diffusion or OpenSW model, you can use text prompt to guide the generation, right? For example, you give a text prompt like a tiger in the forest, and then you will generate something like this. And recently, people are also leveraging diffusion models, injecting the gradient guidance into the reverse sampling process, that you can solve inverse problems. So my group is also working on something like this. So we are solving using diffusion models, like solving inverse problem, like super resolution, deblurring, etc. And also diffusion model can enable human-computer interaction. So for example, if you sketch, you put a skeleton sketch of an object, and you use this control net and put this sketch into the model coupled with a text prompt, then actually you can generate something like aligns with your interest, right? So it can enable all kinds of generation controllability. And also recently people are using diffusion models for video generation, right? This is what OpenAI showed last year, where you can generate something like few frames of videos that seems quite realistic. So what exactly is diffusion models? Actually, the diffusion models has two processes, right? So one is the diffusion process. So the forward process is essentially you starting from some data, and then you are gradually adding noise to the image until it becomes a purely Gaussian noise. And the forward process is basically something like this, where alpha t and beta t is some predefined noise scheduling, right? So you're injecting the noise. And if you this is a discretized version, right? If you make the t really small, and actually this can be modeled by a forward stochastic differential equation, where the f and g are some predefined noise scheduling, and this dw is a Brownian motion that starting from the image and by already injecting the noise, you're becoming a pure noise. But this is something not interesting, right? This is I think it's a trivial process, right? You just injecting noise. But I think the non-trivial part of this diffusion model is the reverse process. So starting from the noise back to the early 90s and more, 80s, and recently by Song Yang's group, they show that actually this forward process can be reversed back. So sorry, and this can be governed like by a backward probability flow ODE or SD in early results. But ODE is usually much faster. People show that solving ODE actually is faster for the reversal. So the basic idea here is that there's a backward ODE that starting from the pure noise, it will reverse back to the original image. But however, here the caveat is that you need to know the score function, right? So if you know the score function, which is the gradient with respect to the x of the probably a log likelihood function at pxt, where pxt is the noisy image distribution at the tth time step, right? So if you look at this, right, so the challenge here is that you don't know the score function. If you know the score function, then you can reverse back, right? But if you don't know the score function, and so that's why actually you need to estimate the score function. If you can well estimate the score function, then you can reverse it back to generate image, right? But there's a challenges. So first of all, the image, we don't know the image distribution itself, right? So image distribution is non-known. And then estimating every time step the log likelihood or the score function seems very difficult. But the basic idea to estimate this is that we know that neural networks are universal approximator, right? If you have large capacity of neural network, you can estimate it well. And that's why actually people, the natural idea here is that let's use a neural network to do score matching, like use a neural network to estimate the score function here, right? And in the early works, like stable diffusion V1 and V3, people are using this UNet based network. Because basically this kind of, you can think it's autoencoder with a long CP connection between different resolutions. And you use a T as a time embedding to control the noise levels for this for score estimation. And more recently, people are using transformer-based models. So, and the reason people switch to these transformer-based models, if you look at more recent versions of the diffusion model, like Sora or Stable Diffusion V3, DALI 3 or 4. So actually, they are using these transformer-based models. I think the reason for people switch to transformer is because they believe that there's a scaling law behind it. So, and another reason is because transformer tokenize everything, right? We can mix the text and the image patch in token embedding space that can enable multimodal generation, right? That's why people are switching to the transformer-based models more recently. And so, okay, so this is good. So we know that actually we can use like a neural network to estimate the score. But the thing is, though, how can we like train the model, right? How can we train the neural network to estimate the score? Well, a natural idea here is that we just do score matching. So we just use a neural network to estimate the score, and we minimize the loss like this. But this is not trackable because we don't know the score, right? This thing is not known. We just want to use this neural network to match the score, but the score here is not known ahead, right? So what we can do about this? Well, this is the idea here is that we are injecting the Gaussian noise. Actually, if you know that you're injecting Gaussian noise, there's a classical Tweedie's formula. So we're in terms of expectation, actually this is equivalent to use your neural network, the score loss. Sorry, that's a score neural network to predict the noise at different levels, where beta t is controlling the noise level. So this is something that we can solve, right? You can just using SGD, like you can draw samples, and then you can draw training sample, then draw noise, and you can run SGD to minimize this score matching loss, right? And but there's a question. So the question is, well, the neural network is a black box model. So why we are minimizing the loss like this? we can learn the score well, right? So, and typically, when you're training the loss, right, you don't have this expectation. You cannot fully, like, you only have finite samples, right? You're minimizing a finite sample loss. So it's not very intuitive, right? We minimize this loss, why the diffusion model can generate new samples, right? It's intuitive that the model might memorize the training data, but why they can generate some samples that are quite novel, that are creative, that are very different from the training data set. This is something that not well understood. And this is about the generalization, right? Why diffusion model is able to generate the new samples that is different from the training data set. And this might also shed light in practice, how can we better control the generation of diffusion models? Because if you look at the text to image diffusion model, right? So the controllability actually is very coarse. You can only like coarsely control the generation, but how about we precisely and manipulate the generation? This is something that we're very interested in. So in this talk, I want to answer the generalization questions and the controllability questions from three perspectives. So first of all, I want to introduce something, a reproducibility phenomenon that is widely observed in diffusion models. And then I will shed some light about generalization, so why diffusion models able to generalize new samples. And then they'll also shed light on controllability. How can we control the diffusion model? To generate something like a precisely manipulate the generation of diffusion models. And if I have time, I'll also tell you some of my recent work on using that to solve some dynamic system estimation problems or data assimilation problems. So first, I want to start with this reproducibility phenomenon that is widely observed in diffusion models. And this is a work actually when the best paper at NIPS workshop on diffusion models 2 years ago. So first I want to start with a question. So for you, so here to introduce this phenomenon, I want to start with a setup like this. So say if you have two diffusion models. So as theta one, you can think of it as a UNet, right? For example, you parameterize your neural net diffusion model as a UNet. And as theta two is another like a diffusion model, which is parameterized by a transformer. And then you train the two models on the same data set. You have the same training data set, which is finite, but have enough samples. You trained it and you trained it well. You train it until convergence. And so once you train these two models, you are going to use the same noise. You randomly draw a noise from Gaussian, and you input the same noise to both models, and you generate the samples follow the same ODE sampler that I described previously. And then you generate two images, right? The image one is from model one, and image two is from model two. And my question is that are they similar or dissimilar to each other?
Well, should be similar if they represent the same distribution, right?
Yeah, exactly. So this is called reproducibility phenomenon. So our observation is that even these two models are parameterized in different ways, and they train using different laws. Actually, they generate very similar images. And this is actually very different from GAN and VE, which I will tell you later. So this is called reproducibility. So if you look at the generated images from different, this is like a more comprehensive visualization of the image content, right? So if you look at the generated images, so each index is denoting using the same noise for generation. And you can see that actually the generated images are looking very similar to each other, where even you use like a different neural network architecture. This is a UNet, this is a transformer base, and this is using different training laws for this is consistent training of diffusion models, right? And then you can see that actually the generated images are actually pretty similar to each other, like if you ignore the fine details.
Are all of these models unconditioned?
Oh, this is unconditioned, but in conditioned case, there also this kind of reproducibility as well.
Are they also trained with the same noise coming in?
You don't need to. So you just train on the same data set.
Same data set, but the noise is different random across.
Yes.
So the ODE is also deterministic.
You can use SDE, I think, but if you use SDE sampling, basically, we'll go back. So you can use SDE reverse sampling, but if you use SDE, you start from the same noise, and for the two models, every time you inject the same noise, then actually the generation is also the same, yeah. So this is a visualization, but then how can we quantify this, right? How can we like see that how quantitatively study this phenomenon, especially how this is related to the model size and the model capacity, right? So and to quantitatively study this, we're going to use some similarity measure to measure the generated sample similarity. So basically, we have two samples like generated from two different diffusion models. And then we're going to use a neural network, which is a self-supervised neural network, to map it to the embedding space. And we measure the similarity in the embedding space, because the embedding space is better getting rid of certain like color scaling issues, which is more robust to measure the similarity. And then we're going to use this metric cosine similarity to measure the similarity between two samples. But how about we measure reproducibility between two models, right? This is only a measure of two samples, right? And then we're going to define a probability measure. So basically, we set a threshold on the generated samples from two different models, which is larger than 0.6. Then we'll measure the probability of the generated samples between two different diffusion models to measure the reproducibility between for example, theta 1 and theta 2. And in practice, we can estimate this probability by using, like, say, many samples, right? For example, we draw 10,000 like noise, and then we can generate images, and then to estimate this probability measure, right? This is a probability measure between 0 and 1. And you can imagine which when the reproducible score is more closer to 1, you have a very high reproducibility, right? And then we plot the simulation matrix between different models. You're going to see that actually there's a very high reproducibility between different models, right? Even different architectures, different training laws, sampling procedure, perturbation kernel, right? You can see that there's very high reproducibility between different models. And this is a more comprehensive study that actually we did a lot of study on many different architectures, and actually the representation is pretty high. But unfortunately, if you look at other type of generative models like GAN and VE, and when you train different GANs on the same data set and draw samples, the same sample, input the model to generate the images and compare reproducibility, and actually for GAN and VE, the reproducibility actually is very small. So which means that actually this is it's rare in other generative models, but actually quite prevalent in diffusion models. So when archiving, publishing our work, actually we see there's a concurrent work from NYU, which is from Errol Simoseli and Stephen Malat's group, that their work actually get this kind of actually the work is very complementary to ours, but their work get a clear outstanding paper award last year, but our paper get rejected and cleared. So what they observed actually is very similar. So what they observed is that they are not training on the same data set. They are training, so say if you have a FFHQ data set, face data set, you're gonna to split the data set into non-ordered subsets. Like this S1 and S2 are two subsets of the whole training data set. And they don't overlap with each other. And you train the same model on S1 and S2. And then the N here is denoting the number of training samples. What you observe here is when the model is trained, right? You use the same sampling procedure as ours, and then you give them the same noise. You see that the image generation is like this, with respect to the training data set, right? So we're going to observe this row 2 and row 3 is the trained model on two different subsets. And when N is very small, right, you will see that the first row is showing you closest image in the training data set. And the fourth row is showing the closest image in the training data S2. And what you're observing here is that when n is very small, right, your model is memorizing your training data set. But the surprising thing here is that when you're increasing the number of training samples to be very large, actually the two models will be generating the same image, which is different from the training data set, right? This is quite surprising because the two models actually are trained on non-overlapping data set, right? But why they can generate the same image, it seems not very obvious. They must say something about the generalization behaviors of diffusion models, right? They are generating something new, different from the training data sets, and they reproduce with each other. Right.
For the second row and third row, you still start from the same noise.
You start from the
Sample.
same noise,
Okay.
right? You're starting from the same noise.
Closest image to the noise field is in pixel space or in something like.
Yeah. You can use either pixel space or I think they are in the pixel space to find the nearest neighbor in the training data set.
But I guess your data set has to be large such that even you split it into two, I think you can still meaningfully learn the distribution of the underlying data set.
Exactly. So that's why actually the diffusion model can generalize because they are much better approximating the underlying distribution. But if you look at GAN, VAE, they are not learning the distribution well, and that's where they don't have the reproducibility and this kind of phenomenon. And really, if you look at the experiment we did here, we are all doing very large data set. We are trained the model on very large data set, but still they don't have this kind of reproducibility in GAN and VAE. But diffusion model seems like learning distribution much better. So this is something that I want to shed light on next as well.
One more question. So this synthesized woman on the far right column, is there something like her in either of these data sets?
Oh, sorry?
Is there something like her in either of the original data sets?
Like
this woman presumably does not exist.
Yeah, I think this is they just find the nearest neighbor in the training data set. And actually there's no such object in the training data set. They generate it.
There's no, okay, but this is the nearest.
Yeah, this is the nearest neighbor in the training data set.
To the noise image, not to the output image.
To the output image.
Oh, it is the closest to the output.
Yeah.
Okay.
So the first row and the fourth is the closest image in the training data set. So this means that they are generating something new that is different from the training data set. So we also quantitatively studied this through the reproducibility. So we did similar, but complementary is that we are training on the same data set, but we are using different models to compare reproducibility. And what you're gonna to see, this curve is showing you that the x-axis is the size of the training data, right? And the y-axis is reproducibility score. And what you find is that in our setting, so we have high reproducibility when you have limited training sample data. And then you increasing the training data set, right? The reproducibility actually diminishes. You don't have reproducibility. But suddenly, when you're further increasing the training data set, the reproducibility re-emerges again. So I think this region is very interesting because I think this is shedding some light on the generalization of diffusion models, right? And that's why actually we did another experiment. So under the same setting. So here we introduce a different score, which is we are calling it a generalization score. And the generalization score is basically to measure when you're generating a new sample X using diffusion model, and then you measure the closeness of the sample to the whole training data set. This is also a probability measure. So if X is close to any one of the training data set, then this generalization score will be close to 0, which means that we're memorizing. But when X is very different from any of the samples, then the score is closer to 1, then this is a generalization, right? So if you put them two figures together, right, you're going to say something quite interesting, right? So, and reproducibility is large in the memorization and the generation regime. But you'll see that for the generalization, right, there's a phase transition there, right, from memorization to generalization, right? So when your training data set is becoming larger, then actually your diffusion model, actually there's a phase transition from memorization and it enables generalization, right? So actually diffusion models, a training diffusion model has different regimes depending on the model capacity and training data set, right? When you have a large enough training samples, the model fail to memorize, and then they start to generate something that is very, very meaningful and different from the training data set. In the meanwhile, they still have reproducibility, right? Means they are learning something similar, right? All different models actually learning something similar in a meaningful way. Right, so that's actually this interesting phenomenon leads us to think about generalization. So why diffusion model is able to generate new samples or novel samples in a similar way, right? So when they parameterize in different, like say transformer or UNet, right? Why they can generalize. And I think a sufficient condition of involve generalization is all different diffusion model, no matter how you parameterize the model, right? So basically they are learning the same score functions, right? They are going to learn the same score function, and then you follow the same ODE sampler, they're going to generate something similar from the same noise. But there's a question, right? So so the question is that there's two regimes, which is one is memorization, another is generalization. So this also means that depending on the model size and the training data set, so diffusion model actually are learning different score functions or different distributions in different regimes. So how can we understand what distribution actually are diffusion models learning? So you might imagine, right? So in a memorization regime, the diffusion model is learning this multi-delta distribution. So basically, this is the distribution of your training data set. Right? Your training data set is a multi-delta distribution. Like this yi is a training data point, and this is a multi-delta distribution, characterize your training data set. Right, and you can imagine in the memorization regime, right, when diffusion model memorizes, then they're gonna to learn this multi-delta distribution, right? And they're going to learn this distribution. And that's why diffusion model are reproducing, and they are also memorizing, right? All different diffusion model, when you have a very large capacity, you're going to memorize those data points. And you can imagine, right, for generalization, right, diffusion model maybe because the interpolation that this empirical distribution going to approximate the underlying distribution. And in that sense, if we can approximate the distribution well, like epsilon close, then we involve generalization. We're going to generate something new. But there's an issue here, is that when the empirical distribution to interpolate the true distribution, there's a curse dimensionality there. So you're going to use many samples, like exponential many samples, depending on the dimension of your data, right? This doesn't seem to be possible in practice. For example, if you train your model on a safer data set, right? So that the D gonna be like say 10,000 something, and then this number of samples you need gonna to billions or something, which is very large. That doesn't seem to be possible. But if you look at in practice, when diffusion model is able to generate new samples, then actually the number of samples needed actually is only like 10,000 something, which is much smaller than the worst case scenario. So this just must mean that there's something like quite interesting that we didn't understand what's going on here. So from my perspective, I think the reason the diffusion model doesn't suffer from this curse of dimensionality is because the diffusion model are not learning arbitrary distributions. They are learning this kind of a low dimensional distribution. Like the images are lying on some low dimensional manifold, right? So if you're learning this kind of a low dimensional distribution, then so that the number of samples actually is not just scaling with the ambient dimension, it's gonna to scaling with the intrinsic dimension of your data. And that's why actually the diffusion model doesn't suffer from this curse dimensionality, where you have finite number of samples, you're going to learn the distribution well, and then you're going to generate new samples from this. So I'm not going to go very much detail in this. So basically, what we showed here is that we try to measure the intrinsic dimension of image data set. So here, what we did is that we consider a denoising autoencoder formulation, where we are using a neural network to directly predicting the Qing image based on the treatise formula. And what we find is that if you calculate the Jacobian of this DAE, like neural network, as it is a neural network to predict the Qing image, and if you calculate the Jacobian of this DAE respect to the noise level xt, and then you visualize the rank of the Jacobian, actually you're going to see that this Jacobian is a pretty low rank in the middle, where this is where the x-axis is showing you the different noise levels, where higher SNR is closer to image and the lower SNR is closer to noise. And this y-axis is showing you the ratio between the rank of the Jacobian divided by the total dimension of your pixels. And what you see here is the y-axis actually is in a log scale, right? And you can see that this Jacobian actually is very much low rank in the intermediate noise level, which I think is corresponding to the intrinsic dimension of your image data set, right? So the intrinsic dimension of your image data set actually is pretty low, right? And that's why actually the diffusion model actually the number of samples required actually is scaling with the intrinsic dimension rather than the ambient dimension of your data that enables the generalization of diffusion models. So, and also there's more recent work that's arguing that the intrinsic dimension of image data set actually is pretty low. So this is a experiment did by Tom Gunstein's group, right? They measured the intrinsic dimension of different data sets. Actually, even on ImageNet, the intrinsic dimension is 140 or something. So which means that actually the intrinsic dimension of the ImageNet is much lower, that you can use some finite samples to enable generalization of diffusion models. I think, and then we built some theory on this. I think maybe of interest of time, I will just quickly go through it. So basically, we started the distribution learning, distribution recovery of mixture low rank Gaussian distribution, because image distribution is very hard. It's very complicated, right? We don't know what image distribution is. So if we want to understand generalization, how diffusion models scale with the intrinsic dimension of data, so why not we assume a simple ground truth distribution, which is this mixture low rank Gaussian? Well, you can think this is like just the union subspace models that sample are drawn from the union subspace, and then for each subspace, the sample are following degenerate Gaussian. And based on this, actually, it has closed form solutions for the posterior mean estimator. And also, we just using the training data set to construct the score functions, assuming that the data is following mixture Gaussian, right? And then you construct the score functions by estimating the mean and the covariance by assuming a Gaussian. And then you construct the score function. And once you use the same noise to generate the samples, and you can see that actually the generated samples on simple data sets like flash MNIST and MNIST, right? You can generate something that's pretty close to the real diffusion models, right? And this is something that you didn't learn, you just construct it. But for CFAR and FFQ, right? Starting from the same noise, you're going to generate something close, but you lose the fine details there, which means actually mixture Gaussian actually is a coarse estimation of the image distribution. And we also developed some theory, right? So we can show that actually if you parameterize your neural network according to this optimal posterior mean estimator here, you're going to show that when K is equal to 1, when you have, like, say, only have one mixture, you can see that this training loss of diffusion models actually is equivalent to PCA problem. So we're going to show that there's an equivalence between training diffusion and PCA problem. And then you can characterize the sample complexities, right? You can show that how many samples you can enable generalization, you can learn the distribution or learn the mixture Gaussian distribution. And so when K is larger than 1, right, you can show that actually training diffusion models is almost equivalent to subspace clustering problems. And then for each subspace, right, you have enough samples, and then you're going to enable generalization of diffusion models. We visualize the phase transition there, right? So how many samples we need to learn the basis for PCA and for diffusion models, for subspace clustering and diffusion model, right? The phase transition here seems to be quite similar. And this is a theory part, but I think the more interesting part of the work is that if you know that diffusion model is behaving much like PCA, right, this can enable us to better manipulate the generation of diffusion models. Because if you look at the PCA, right, you know that each basis of each column of the basis has semantic meaning, right? If you can manipulate the basis, then you can manipulate the generation of diffusion models by controlling it in a disentangled and in a disentangled way. So here is an illustration of how we manipulate the diffusion model generalization through such an understanding, right? You can, through understanding that this is a more behaving like a PCA, then if you can manipulate the generation, like for example, this U1 and U3, U4, they are the basis of the Jacobian. And then you manipulate your generation along that specific direction, you can manipulate certain attribute in the generated content, right? For example, if you manipulate along the U1 direction, you're going to change the gender. And then there's another direction, you're going to change the color, the head, here, etc., right? And this leads to the third part is that actually we can, through this understanding of generalization, you can enable this kind of manipulation of the precise control of your diffusion models. Like you can develop a learning-free method that can guide and manipulate the image editing or control of your diffusion models. And first of all, I want to show you some results. So the proposed method is called low-rank controllable image editing method. So basically, we can manipulate the generation. For example, if you have some images, you can manipulate the mouth shape. You can manipulate the hair curvature, the hair mount, eye shape, etc., and in a very interpretable way. And moreover, we find that this editing direction, once you find, actually is transferable and actually is homogeneous. For example, if you find editing direction on one image, and then actually you can transfer the editing direction to the other image and to different noise levels as well. And moreover, this editing direction actually disentangle and they can be composed with each other. For example, if you find editing direction that one direction can edit the eye size, another editing direction can change the smile. And then you combine them together, right? They're going to change the eye size and smile at the same time. But the other part of the image actually is keeps the same, right? It didn't distort other part of the image, which is cannot be achieved by existing control methods for diffusion models. And also the editing direction actually is very linear. So if you change the strength of the editing direction, you're going to change the open mask to closed mask, right? And this is a linear change of the editing strength. This is for unconditional diffusion models. And actually, you can also make this work on text to image diffusion models. Like, for example, if you give a text prompt, like here up, and then you use our method, you're going to change the here, the ear, and you're going to add a glass, right? This is something that actually not existing in the face, but actually you can add a glass and add different here curving hairs, but which doesn't exist in the original image. And using some guidance through the text prompt, you can enable such editing of the images. So how we achieve this? So next, I'm going to tell you a little bit of the basic idea that how we achieve this manipulation of the diffusion models. Well, the basic idea is you look at this posterior mean estimator. This is something that abuse the notation a little bit, right? So previously we called this X theta, but here we are using a score matching loss. And this F theta is almost the same with X theta I introduced in the previous section. So this is F theta is a posterior mean estimator that is a mapping from XT to the clean image. We want to look at into this mapping to understand how can we manipulate the image. And what we're going to do is that we're going to look at the first order Taylor expansion of this posterior mean estimator, this mapping. And we're going to look at the first order Taylor expansion of this mapping at the time step xt. And we find that actually this first order Taylor expansion has some very nice properties. So there are two key properties that enable this kind of local edit of our method. So one property is that we find that this first order Taylor expansion actually is pretty linear. So actually is a well approximation of the posterior estimator. In other words, the posterior estimator itself is pretty linear, right? Yeah, if you look at the cosine similarity between F theta and L theta, actually the cosine similarity is almost equal to 1 for most of the time steps. So which means actually we can manipulate like almost on the first order Taylor expansion part to manipulate the image generation. The second part of property that enables the generation is controllability is the Jacobian, right? This Jacobian matrix actually is pretty low rank. But this is something that already showed in the previous section, right? So the Jacobian actually have this kind of low rank curve, right? So although closer to noise and closer to image is high rank, but in the intermediate time steps, actually the Jacobian is pretty low rank. And that's why actually we are going to do one step editing at the intermediate time steps where the Jacobian is very low rank. So, and then based on these understandings, how we like control or manipulate the generation is something like this. So first of all, you compute the Jacobian, right? And then you do a singular value decomposition of this Jacobian matrix. And we know the Jacobian matrix is low rank, right? We can use something like a generalized power method, like to compute the compact SVD of the matrix. And once you compute the decomposition, you're going to use one of the right singular vectors to control the generation. Because if you use delta x is how you're editing your image, right? So you're going to use one of the right singular values, singular vectors, and then you're going to hit, and this is the equivalent to hitting the Jacobian with this vi. And we know that vi actually is orthogonal to each other, right? It will be canceling out most of the directions and only living with one direction of ui, right? Ui is a left singular value, which singular vector, which has semantic meanings, right? And then you're going to control the generation through this vi. And so this is a basic idea of our method, right? And this is a more a generic pipeline of how our method works in detail. And if you look at identify the direction of controlling our generation, right? You're going to see that the find directions indeed have semantic meanings, right? They're corresponding to eyes, lips, airbron, nose, dog hair, etc. And we also did some comparison with some existing methods for controlling the generation, right? This is a comparison with all the state art of control the editing methods for diffusion models. And the last row is column is our method. You can see that actually here we are adding a red lipsticks to the face. But you can see that our method actually is only changing the mouth, the lipstick, right? The lip. But if you look at all the existing methods, right? So actually they are significantly distorting the image. And for this blend diffusion, they didn't distort, but sometimes they didn't add the desired lipstick to the image, right? But our method is more consistent. It can add the lipsticks, but with not distorting the whole image, right? We can enable this kind of local low rank editing of the images.
Right. It's a good question. So, you have the singular vectors that have semantic meaning, but how do you know which one is the lipstick?
Yeah, that's.
Maybe you mentioned that and I missed it, but.
Yeah, because our method is basically doing SVD, right? So there's no like a supervision there. So we need to do interpretation afterwards. So you find the basis and then you visualize it, right? Then you know which direction you're going to edit.
So that basis is in the image space or in the latent space?
In the image.
Or in the image space?
Yeah, because the column of this view actually is an image.
You just plot what the basis looks like, and it looks like red lips, or.
You go, yeah, it looks like the lip, and then you're going to control that. Yeah.
Wow.
Yeah, and then you need to do post some interpretation.
Presumably they're well separated because
Because
these phenomena happen at different rates in the data set, and therefore they're associated with different singular values. But
Right.
but if you had two things that happen pretty much the same amount, like crow's feet around the eyes and a smile, which are highly correlated,
I see.
would you expect to see them combined in one singular vector?
Here actually we are using this kind of low rank. So here we are not editing at we're editing at a time step like which is equal to like say t equal to 0.6 or something. And actually we are just using like r equal to rank is equal to 10 or something. But most of the things that we find there actually is quite disentangled or orthogonal to each other. We only find the dominant singular values, singular vectors. But I think maybe one way to extend this method is to learn a concept dictionary. Like for example, you consider this dictionary learning method, right? Maybe you can use multiple images. Here we are only doing this on single image, right? What if we have a multiple image and then we can do this kind of singular value decomposition and learn the basis and maybe extract some common structures using dictionary learning and then to interpret them.
Yeah.
I think that's something that
And
could
and
be.
also, it appears to me that some of these changes are correlated with brightness changes on the
brightness.
face. Is that because of the linearization?
So which parts?
Well, here you can see it, but even going back 5 or 6 slides.
Yeah, this
Yeah.
one.
Oh, yes.
A lot of these are,
So no, this is a mask. Actually, we also we able this.
no, not the
to-
mask, I just, between the second and the third images and all
Oh,
of these,
yes.
there are brightness changes.
Yes.
Not necessarily a flaw, I mean, it just could be that the singular vector was applied with. I assume you've removed the DC component.
Right.
So if you exaggerate the singular vector, then it makes sense that some parts will get darker and lighter.
I see.
So just brightness, so if you look at the picture of the cat, there's like some green vegetation that showed up the ears up versus the.
Yeah, so this is a text to image diffusion. I think the text prompt might also disturb the generation a little bit. This is a text condition generation.
The mutation in ears up could be highly correlated in the data set, right?
Yeah.
That's where you see animals.
Yeah.
Domestic animals have floppy ears, but wild animals have.
Yeah, so with time left. Okay, I don't have much time left. So finally, I want to just briefly mention that actually this idea actually can enable watermarking as well. So if you look at, actually, there's a lot of work by Tom Goldstein's group that trying to watermark diffusion models. What they did watermarking is that they're gonna to watermark the image in the high noise level, right? So if you just do a Fourier transform of the image into the frequency domain, and then in the frequency domain, they will be cropping a part of the frequency and inject the watermark into the image, and then they generate the image. And this is the generated image compared to the original image with the same random seed. You're going to see that actually the generated image is actually a highly distorted. And I think the reason for this is that if you look at the rank curve here, right? There's a Jacobian rank curve. And when you injecting the watermark in the high noise level, the Jacobian is almost like full rank, right? So actually they're going to distort your image significantly. So instead we introduce a method called this method that instead of injecting watermark in the high noise level, we are going to inject the watermark in the low intermediate noise level. And the reason for this is that if you look at the rank curve, that here is intermediate timestamp is pretty much low rank, right? And we're going to inject the watermark in the null space of the Jacobian. And the null space actually doesn't change the generation. And you can think that actually there's dual part, right? So the Jacobian itself, we can utilize this for controllability. And the null space going to be, we can use that to do watermarking. And that's why actually we can develop a new watermarking method that is actually almost invisible. And also we have some methods to detect, robustly detect such a watermark, which, yeah, I will not go into the details.
Sorry, just in principle, I could go back and reverse the process and remove your watermark, right? And regenerate the image, given that they're reproducibility.
Right. Yeah. So we're actually using DDIM to implement this. Actually, we can also.
You're using what?
DDIM.
Okay.
So DDIM inversion to get, and then you can remove that. Yeah, exactly.
So the fact that there's a phase where it is lowering, does that mean that these data sets are intrinsically low variation?
I think the model, the diffusion, some people are thinking maybe there's some smoothness, and people are actually trying to, more recent work, trying to construct the score function directly from the training data set. Or they think that, okay, so there's so they're also thinking to understand generalization. There's a lot of recent work trying to understand generalization is, so you can think the training data set is like this kind of very spiky distribution, right? So you think this generalization might be enabled because when you're training your diffusion model is learning a convolution, trying to convolve this empirical distribution with something smooth. And that might be the reason enable generalization as well. But we are also thinking there are different perspectives to look into this.
Just a naive mechanical question. Are these graph neural networks, are you predicting a single pixel given some reasonably large neighborhood around it, or are you predicting the entire image?
I didn't quite understand.
I mean, are these, so is this network specific to a particular resolution of images at a particular scale?
Yeah, we are training on particular skill.
Yeah, but when it generates an image, can you say generate me 1,000 by 1,000, 2,000 by 2,000?
No, I think we need to stick to the same.
So you are generating a single image in one fell swoop.
Right.
But I think diffuse still have like cascading, right?
Yeah,
They actually train like, I don't know, like that base image from the diffusion model, and then they just use the super resolution, just scale up to higher resolution.
But that's using a different process.
That's
no longer
different process.
using the
That's
diffusion
different
itself.
process. Yeah.
So the low resolution one becomes what
From
you
the
could
data.
consider to be a latent representation, and then you're expanding it.
Yeah.
I mean, I'm asking just to get an idea, is the diffusion process that's being modeled fixed to a certain regime of scales in images? Like, you're not training on.
Typically, we're
close-ups
training
of
on
face.
the same skill, and then we
Same scale,
generate
right.
the same skill.
Sorry, just a follow up. So again, this is the rank of the Jacobian of the score function or of the network.
At X, the posterior mean estimator. It's not a score. So there's a treatise from
The posterior mean estimator, fine, but then
Yeah.
you're just subtracting a constant from that. So ultimately, it's still looking at the Jacobian of the network itself. That's
Yes,
really the main
yes.
component.
Right.
Well, but these could even out. Sorry, what I was trying to ask is, if you were to extract out the XTs at that intermediate step, at the T equals 0.5, 0.6,
Oh.
And look at the rank of the entire data set.
I
You know,
see.
vectorize the images, look at the rank of the data set. Do you see a consistent behavior where at some point these intermediate XTs have, does the data set have an overall lower rank for these intermediate XTs compared to the original images that are given to the data set?
Mm. I see. So you're gonna to like do a, like say for example, PCA of that. So how, I mean, you mean that on XT, right, you collect all those noisy images
Right,
and you want to do some like PCA or
right.
to. Okay. Yeah, we haven't looked into that. I think the original images could have these kind of local low rank structures, but I feel the XT might not. And that's why actually
Yeah, it's noisy.
yes,
It's
noisy.
noisy.
Noisy is gonna be a problem, for people, right?
Yeah.
But certainly if everything's photographed at the same scale in the training set, then it's been known for 40, 50 years that it's gonna be low rank, particularly for faces.
Mm.
Eigenfaces, right?
Yeah.
I mean, it does remind me of eigenfaces, because they had that, the eigenvectors were like eyes and faces.
Yeah.
No, just.
Yeah.
Okay, so yeah, I'm gonna to stop here. I think we're at on time.